Next, I'd like to introduce Marketa Jansova from Solaris. She's going to speak on quality assessment of global tilted irradiance by automatic and manual procedures.
Okay, thanks for the introduction. Okay, so let's dive into the topic. So as usual, I need to start with some motivation. How this should work. It's not moving. No. I need to click. Okay. No. Okay. Perfect. I figured it out, and I have Mac as well. Fine. Sorry. Okay. So why ground measurements? Ground measurements are essential for development and operation of PV plants, as you know. So what we can use it for? We can improve the satellite-based model with it. We can improve our forecast accuracy, PV performance evaluation, or even we can identify PV operation issues using ground measurements. Okay, a little bit more about ground measurements. So from our experience, what we see that there is quite a missing knowledge about the proper operation. The practices are somehow not really optimal. And measurements are very, very often degraded with some issues like shading, soiling, or here even in pictures you can see some frost and snow on the parameters. So what we can recommend, the best practices are that there should be usually more than one instrument on the site, so you can double check. Also, you should choose, high quality instrument. What is also good is to have a fine temporal resolution, so it's better to have 1 minute or 5 minute data than hourly data. And then regular cleaning, regular maintenance, calibration, and just the care of trained personnel. And it's also always good to log when this maintenance happens, so we can easily see that in data. Okay, and last but not least, data quality assessment by knowledge expert is very important. All right, so this was generally to measurements, but today I wanted to speak about GTI, global tilted irradiance. And why? Because every bigger PV plant has typically several GTI instruments. And what is very important, these instruments these measurements are used for PV performance evaluation. And they can also be used for validation and adaptation of models. All right, so if you want to use it for PV performance evaluation, we need high quality GTI measurements to get some reliable results, right? So what basically we want to achieve is to measure these raw data and make a reference data from them. And from our research we did recently, there is actually not really much knowledge and standards and procedures for GTI quality control. So what is the current status? What we have is that we have some existing published knowledge about GTA and quality control. We in the company, or even worldwide, we have some experience with GTI. And also we have some existing methods, procedures, and procedures for global, direct, normal, and diffuse irradiation, so GHID and diffuse. So what in Solaris we do for GHID and diffuse is, several steps of quality control. So first, what we need to do is time reference control. So basically what that means is that we need to shift our data to UTC so we can calculate, the solar position correctly. This may sound like easy task, but we always quite often see very weird things in data, like time changes, or even each day with different time shift and so on. Then in the second step, we can really look into quality of data. So first, what we do is very automated test of unphysical values. So we can look for physical minima, physical maxima, static values, night values, and then we can also compare, these instruments against each other. So 2-component, 3-component test. Then once the biggest rubbish is out, then we can look for specific features in automated or semi-automated way. So this can be, for example, shading, as it was introduced before me, or degradation, dew frost, tracker malfunction, or periheliometers, or even instrument misalignment. And then as a last step, you always, like do visual quality assessment, because there can be issues which can be mixed together, or they don't appear that often, or they can be very specific to that site. So yeah, you cannot really automate them, or we are not that far. Okay, so this was GHI DNI diffuse, and what we can do for GTI. So we see that methods and procedures can be largely reused. So we can base, our quality control on these parameters mentioned before. But there is additional complexity, of course. And what is it? So GTI, you can have fixed or tracker systems. You can have some inherited PV features, for example, parking or stowing position, because the sensors can be, the instruments can be often installed on PV panels. So yeah, like they inherit the behavior of them. Then you need to take into account tracking configuration, which actually doesn't need to be really correct. And then what is important, that because your instrument is tilted, you don't see the full sky dome, and you also have a reflected component. So you bring albedo to the game, and everything gets much more difficult. All right. So let's start with these steps for quality control of GTI. So as I mentioned, always the first step for us is not really first step, I will talk about it later, but what you need to do is time reference check. So basically, as I said, you need to, like shift your data to UTC, or at least, like we do it like this. So you can see it in the bottom plot, where you see, like original data and data after shifting. Why we need it in UTC, as I said, this data determine the solar position calculation. And how we detect time reference shift, we do it completely automatically by looking when the day begins and ends. And also we look at the clearness index symmetry between morning and afternoon, which you can see in the top plot. Yes. And unfortunately, the day begins ends for all instruments at the same time. So we can reuse same logic for GHI, diffuse, GTI, both fixed tracker. So this is no problem. But then, things start to get more complicated, and we need to do instrument configuration check. So basically, for GHI, there is nothing much to do, because it's, like instrument which is installed, parameter which is installed horizontally, and there is no configuration really. Only thing which can happen is that somebody doesn't install it completely horizontally, and the instrument can be misaligned. So what we developed for GHI is misalignment tool, which tries to detect if the instrument is misaligned, and you basically can see its results on this top plot, where you have azimuth and tilt plane, and the initial and estimation alignment. So this is actually not for GHI, but for fixed GTI, but it's basically the same logic. So as I said, we can use this tool for GTI, but there are more parameters we need to take it into account. So we have fixed and tracker system. We can have trackers which are 1 or 2 axes, and then instead, we need to detect azimuth tilt, but also for tracker rotational limits, backtracking, and so on and so forth. And how we do that? We do basically a multi-dimensional fit via all these parameters, through all these parameters. Okay, so once we know what time shift there is, what configuration there is. I mean, typically the configuration should be, given to you, but we often see that the configuration we get is not completely corresponding to what we see in data. So this is why we need to go through that step. Once we have it, we go to a basic automated test of physical or unphysical values. So what is the easiest is invalid values. So really, like -1000 or something. Sun below horizon, so night values or consecutive static values. For GTI, we used what we have for GHI. Because there is not really any change. So you can see here some examples of sun below horizon or consecutive static values, or even in the invalid values on the left. And then we go to more complex things, which are physical maxima and minima. Actually, for minima, it's quite easy. We say that GTI should be at least 0. But for maxima, things are a little bit complicated. So let's have a thought about this. You don't need to look at the equations. I will try to explain it by words and pictures, which might be a little bit easier. So if you look at the picture on the top, so what can happen? There are two situations. So on the left, you see that we have our tilted instrument, which is in blue. And we have 3 components of solar radiation. So we have diffuse part in blue, direct part in yellow, and the reflected part in red. It doesn't really have to be always like this, because if you look at the picture on the right, like the sun is already behind the instrument. So you can see only diffuse part and reflected part. And actually, like how it looks in data, you can see it in the plot in bottom. So here we have instrument which has a tilt of 90 degrees to east. So in the morning, you are in the situation on the left side, and in the afternoon on the right side. And you can even see it in the violet curve, which is on the plot. So you have all radiation, and then it drops down to lower level because there is no direct solar radiation anymore. Okay. So I try to explain how it works, and now how we can think about physical maximum limit for this case. So for the mornings, it's actually quite easy, because if you think about it, the limit for the maximum should be proportionate to clear sky GTI. So we take some constant times clear sky GTI, we add some buffer, and we are more or less done. But for the right part, when we have no direct solar radiation anymore, things are actually not proportionate to clear sky diffuse plus clear sky GTI. Reflected part, diffuse plus reflected, because diffuse part can be much larger than clear sky diffuse. So here we need to somehow maximize the diffuse up to some, physical or unphysical level, and then at a reflected part. So this needs to have a little bit of thinking. What is also important here is that in the reflected part, there is albedo. And somehow you want to have it, generic across all the regions through the season. So you need to take a maximalist value of albedo. And also what you need to, think about properly is that, okay, you try to detect the configuration, but still there can be slight misalignment or configuration mistake. So you also need to, what we do is actually we vary the incidence angle for this maximum limit. And we somehow take a little bit larger value. So we also take into account the configuration error. Fortunately, we can do the same for fixed and tracker systems, so there is not that much large difference. Yeah, and I hope that it was understandable. If not, there is Slido for questions, and I can try for a second time. Okay, so here you can see some results. So on the left side, there is this physical limit for a fixed system, which is 90 degrees tilt to the west. So here you can see that you have two parts, so where you have DNI and you have no DNI. And in gray, you can see diffuse part. In blue, there is reflected part, and in red, there is buffer. We add, and in green there is solar, so there is this GTI measured. Same thing on the right, but for one tracker system, where you basically have only this area where you have, like the clear sky DNA part. And in the bottom, you can see how this limit worked on one example of data, where you can see in red that a part of was excluded by our physical limit. Okay, so that was physical maxima and minima. And then what we can look into is two-component or consistency tests. So as you know, for GHI, DNI, and diffuse, there is like nice consistency test, but this doesn't really this is not really true for GTI. But what we can do is we can take GHI and calculate GTI from it, and then compare calculated GTI from with the measured GTI. Again, if you have some configuration mistake, you can end up in some troubles, which you can actually see here. So on the left plot, we plotted calculated version versus measured. And you see it's nicely on diagonal, and we could catch some outliers in red. But on the right plot, we injected a wrong configuration, and then you see that the population is wider and not the diagonal anymore. Okay, so we are done with the basics. And now let's see the semi-automated and automated tests and visual assessments for specific issues. So first one is shading. You heard a lot today about shading, so I will not go into detail. And so basically in like 90% cases, we can completely automate it by plotting our data in sun azimuth, sun elevation plane, as you saw today. And then you can get there to populations of shaded and unshaded data. And then it's just a task of distinguishing between these two populations, which we do by kind of clustering. Okay, then another issue which you can see in data is your frost. Again, our approach for GHI is that usually on parameters we see this S-shape curve and we can detect it, and in a limited way we can do it also for GTI. Then we have other issues like degradation because of insufficient cleaning or calibration, logger issues, bird droppings, and so on. And now we mainly distinguish that by a visual assessment. We have partially automated this, but these are really, like things which we can hardly see automatically, but working on it. It will be doable at some point. Okay, so this was something we already have for GHI. We tried to apply it for GTI. It worked somehow, partially. But in GTI, we have other issues which are not present for GHI. And as I mentioned before, they typically arise from the instrument installation. So this can be parking or stowing position or tracker malfunction for tracked systems, where we can actually we detect it using a satellite-based model data. Because when we have parking position, our GTI basically goes to GHI. And then also we have other parameters, as I mentioned, configuration parameters, row spacing, rotational limits, and so on. And we are detecting these via this big configuration fit at the beginning. All right. So I was speaking about methods for quality assessment, but I think, you know, like this is not enough mentioned, that there are, you know, like these small things which are around, which could make our life easier. And this is, for example, parameter type detection. So we usually get some data in Excel claiming, you know, this is this parameter, but we find out that it's different parameter after some time. So we try to think about it and automating this kind of detection. Then also we sometimes see that you know, the data column is mixed from more instruments. So we have half a year of GHI and then it just swaps to GTI. Or sometimes units are wrongly given and so on. And also what really helps us if we have more instruments and we can do multi-instrument analysis to somehow like have more understanding of what happened. So this is in orange because we are working on these things, but not everything is completely done. And then another thing we just didn't have time to deep dive into, but we always also often see it in data that coordinates are not correctly given. So not enough digits, wrong coordinates, minus instead of plus or something like this. Okay, so now more practically, where you can see this kind of tools is our software, desktop software, which is called Solaris Analyst. We gradually introduce these tools there. You cannot find there everything because first, you know, when we produce something, we have it quite a long time in our internal production for testing, improvements, and so on. But, you know, in each release, there is something new. And this desktop software was designed specifically for this community. It can do quality assessment of data, data management, data visualizations, and analysis of measured and model data. And on the right side, you can see some examples from this software. All right, so I'm finally at the end. Yeah, as I mentioned, GTI, Global Tilted Irradiance, is widely used for PV performance evaluation, but these measurements are often suffering from many issues and poor maintenance. So this is why these GTI measurements need to undergo very strict quality assessment to get accurate PV performance. And as we see, there is a lack of tools, standards, and procedures for GTI quality control, but they can be developed. Okay, thank you for your attention.